This is Chapter 9, Optimization, a special variety of equilibrium analysis. So in the previous chapters, we learned a lot of things about the derivatives, right? So in Chapter 9, we'll apply the concept of derivatives, and we'll see how we can use the derivatives to find out the optimization values of a function. So first, let's talk about what is optimization, optimum values and extreme values. Okay. So extreme values are very easy to understand. It just means the maximum value or the minimum value. Right? So if I give you a function, this is y, this is x, which is a very random function, right? So the range is from 0 to x0, for example. So this is a range, right? And I give you a random function like this. So I may ask you to find the maximum and the minimum value of y given the range of the x. Okay, so if you don't know how to draw the graph in a plane, then it's very hard for you to find that by just thinking about that, right? So we'll talk about how to use the derivatives to find out the maximum and the minimum value. Okay, and for the optimization or optimum values, it means that to find the set of values of the choice variables. We'll talk about that later on. Here, choice variable. So find the set of values of the choice variables that will lead to the desired extreme values of the objective function. So this means that sometimes for a function, we want to find the maximum value, or sometimes we want to find the minimum value, right? So if the maximum value is what we want to find, then the maximum value is called optimum value. But if the minimum value is what we like to find, then the optimum value is the minimum of the function. So for example, so suppose our goal here is to maximize the profit of our company, and we use pi to denote that profit. And we have an objective function, which is a function that's related or can be defined for the pi. So the objective function is a function that related to pi, which is pi equals to r minus c. So r is the revenue and c is the cost. Right? So this is a very simple expression to find out the profit, right? So profit meaning that means your revenue and minus your cost, which is your profit. And the choice variable here in this example is Q. And the Q is the quantity, right? The quantity of goods that you produce, right? So this is called choice variable because Q is a independent variable of all the three things here. So for pi, r, and c, all of that can be expressed as a function of Q, right? As a function of Q. So if we determine what Q is, we can determine the level of pi, r, and c because all of them are related to Q, right? So Q can actually determine the pi, r, and c. So this is called the choice variable. When we choose the variable Q, we then choose the r value and c value, and then finally the pi value. So here in this example, the optimum value or the optimization level of pi is just the maximum value, right? Because we want to maximize our profit. So the maximization of pi is our optimum value. And in general, given the function y equals to fx, Our goal is to find the level of x that will maximize or minimize y. So sometimes we want to maximize or sometimes we want to minimize. I suppose our goal is to minimize the cost c. Right, then the optimum value in this example is the minimum of the cost c. Okay. And here we have a very critical assumption, is that the function f is continuously differentiable. So continuously differentiable means that the function f, if you draw that in the graph, it should be continuous. Right? Continuous means this thing. Right? So discontinuous means it has a jump, right, somewhere in between, in the range of x. Right? Or something like this. Right? There's no value between them. Anyway, so this kind of things is called discontinuous. And a continuous means we can draw a line or curve, a curve or straight line or something like that, continuously, right? So this is continuous function. Or by definition, the continuous function means in the range of x, from 0, for example, to x0, in the range of x, for any x value in the range, we can always find a y that's corresponsible for the x we choose. Right? So y is defined everywhere in the domain from 0 to x0. And it's differentiable everywhere. Right? So if you take the differentials of y given any x in the domain, there is a value of dy. Right? It can be differentiated anywhere in the range, in the domain. Right? Okay. So this is our assumption here. And then we can talk about something called relative and absolute extreme. So here we have 4 graphs. So for the first graph, y is a constant function. So we can write this, suppose this is a, right? So we can write this function as y equals to a. So it's just a straight line and it's parallel to the x axis, right? So it's just a constant function. So suppose we want to find the maximum and minimum of this constant function. We know that it's very apparent to see that the y value is the same everywhere. Right? No matter what kind of x you choose in the domain from 0 to x0, right? No matter what kind of x you choose between 0 and x0, y is always the same. So there's no maximum or no minimum for the y, or we can say that every point is a maximum and every point is a minimum for this function, right? Because everywhere the y is the same. Okay, so if we choose any point here, they have the same value. So this is the maximum or the minimum of the function. And this is also the maximum and the minimum of the function. Okay. So this is the first case for the constant function. For the second function here, we can see that it's a curve actually, but it's strictly upward sloping everywhere. So for this case, we say that y is a strictly increasing function of x. So this means that when x2 larger than x1, y2 also larger than y1. Right? So when x increase from x1 to x2, y should also increase from y1 to y2. Right? So this is called a strictly increasing function. So for a function like this, again, we have a domain from 0 to x0, right? So it's, again, very easy to see that when x equals to 0, this point is the minimum. And when y equals to the largest value in the domain, which is x0, y reaches the maximum, right? Because from 0 to x0, y is always increasing. So that means that here it has to be the minimum, and at the end of here, it has to be the maximum, right? So the absolute extreme means the maximum or the minimum value in the entire domain. So here, this minimum is called absolute minimum because it's the minimum point in the domain from x to x0. Right? There's no point in the line, or there's no point for the function that has a point that's less than this one. And for the maximum here is also called absolute maximum because it's a maximum value for all the y here, for all the y value here in the domain from from 0 to x0. Okay, so this is called absolute extreme. So for graph C, it's not a strictly increasing function, right? Because the function first increases and then decreases and then increases again, right? But we can see that we can reach a peak here and then the trough here. So in the peak here, the value of y first increases and then decreases. So here, this is a little bit peak. We call this the maximum here. Because here, we can find that this point, the y2 here is the maximum value in the range. Again, the range, the domain is from 0 to x0, right? So this point, the y2 here, is a maximum, and the trough here is a minimum, right? Because there's no point that lies below this point. So y1, I call it y1, is a minimum in this graph, right? So in this case, we can see that when x equals to 0 and when y equals to x0, I mean the endpoint of this line is no longer the absolute extreme values, right? Because there's a peak in between and there's a trough in between. So the maximum and minimum value becomes somewhere in between 0 and x0, right? It's not endpoints anymore. Right? So this is a third graph. And this is also called absolute maximum and absolute minimum, right? In this graph. Okay, so for the last one, again, it's not a strictly increasing or decreasing function. And we can find this little trough here and a little bit peak here, right? And suppose the domain is again from 0 to x0. But what is different from the graph D to graph C, is that for endpoints here, the values here, we call that y1, right? Value y1 is larger than any of the points, any of the y values in the range, right? So actually, the endpoint here, when x equals to 0, is the absolute maximum value for the function y in the domain. And for the other endpoint, when x equals to x0, this value y2 reaches the which is the absolute minimum, right? Because this is the smallest point for y in the domain. But here, in the trough here, when x is less than this trough, the value is decreasing. And after that, the value increases, right? So we call this point the relative minimum. The relative minimum. It's not absolute minimum because there's a point that's even smaller than this point, than the trough point here, right? But here we can find that it's a relative minimum because for all the points less than that, the y value is higher than that. And for all the points, not all the points, but for the nearby points that's larger than the trough point, y value becomes larger again, right? So that point, the trough point, the relative minimum, somewhere in between the function. And for the little peak here, for the nearby points less than this point, the y value increases. And for the other points that's larger than that point, y value decreases. So this is called a relative maximum value for the function. It's not absolute maximum because there's a point here, right, y1, which is larger than the relative maximum. So although it's a peak, but it's not high enough to be the absolute maximum, right? So it's called relative maximum here because it's still a peak, right? And for the trough, it's called the relative minimum because although it is a trough, but it's not low enough, right? So somewhere else for the y2, it's lower than that. So we can see that for a graph, if we want to find out the absolute extreme values, we need to find two things. We need to find four things, right? So the first thing is to check whether or not there is any peak in the function, right? And then we need to find out the peak point. So the peak point is a potential candidate for the absolute maximum, right? Although it may not be the absolute maximum, right? But it's a candidate. So we need to find out the peak value, any potential peak values in the function. And then second, we need to find out the trough values, right, in the function because they may be the potential absolute minimum values. And the third, we need to find the left end values of y, right? The left end, which is when x equals to the smallest value in the domain, which is 0 in this example. The y here, which is the end point, is something we need to pay attention to. The fourth one, the right end, which is the maximum value that x can take, which is x0 here. So we need to compare the four values, right? We need to compare, we need to compare the peak values, trough values, the left end values, and the right end values, right? So compare all of them. Okay. So for the graph C, if we compare the four values, we find that, okay, the peak value is high enough to be the absolute maximum. The trough value is low enough to be the absolute minimum, right? But for the graph like D, although we still have a peak and a trough, but they're not high enough or low enough to be the absolute value, right? We still need to compare them to the end points, right? To the right end and the left end points to find the absolute values, right? Otherwise, they are called relative extremes, right? Okay. So in the next videos, we'll talk about using the first derivatives test to find out the extreme values.